So let's jump in after this short advertisement block. I'm Paweł Suchołbiak. As Remek said, I'm a lead software test automation engineer at EPAM Switzerland. I love improvements and food, not necessarily in that order. And of course, I like skiing, cycling, running, and hiking. So pretty much what Switzerland has to offer. So as a warm-up, I would have one request for you. So if you could please all raise your hands, and then I'll be mentioning a few tools. Come on, raise your hands. I mean, it's gonna last 2 minutes and it will be over, I promise. So the idea is that if you use that tool recently, or the technology recently, you'll lower your hand. So I think people are kind of lazy today, so let's do revert. I mean, so let's start with C, SQL, C++, Oracle DB. Okay. Next part, Bash, Java, Python, HTML. Yeah, and the last group I won't even bother reading out. So what those technologies have in common? They're quite old. Like the first group is already 40 years plus. Second group, 30 and 20. So that leads us to believe that we need to start thinking about the future prospects of the tools we're using. So, of course, you can think, okay, this presentation is about Git, so how it correlates. So Git is not the youngest one. It's already an adult, 18 years old currently. And would it be replaced? I'm pretty sure yes. However, it's not going to be overnight. So generally, there should be a contender already in place. So Stack Overflow in 2022 did a survey. So I've just extracted the results from the professional developers. And here, Git is crushing. So there's no one on the market yet who will be kind of already pushing out the current leader. And on top of it, are we safe? So Git definitely might have some challenges. So is it the history? Like, what will happen with our projects after 10 years, after 15 years, after 20 years? Should we start thinking about the change already, or not yet? What about the code base, that it's basically huge? What if we have 1 million of the files in the repositories? What if there are tens of thousands of contributors, like the Linux kernel? Like, what will happen then? Or basically, what about the access control? Git generally doesn't care about the access control. If you have access to the server, you are welcome to fetch whatever you want. So, testing Git, and that's kind of complicated. What we would like to stress test, is it the command line? Is it the GitHub, Bitbucket? Or it's a plugin from IntelliJ or VS Code, or interface? And now the question is, what the heck is the interface with Git? So Git has multiple implementations already. So we have native command line Git written with C, but also we have multiple other implementations. And the tricky part is that they all need to basically be interchangeable. So if I create a repository with JGit, it will work the same as when using native C. So what we should choose here? So again, back to Stack Overflow, they did another survey, and they asked people about the tools that they prefer to use when controlling their repositories. And still, majority of the people are choosing command line. So is it a normal project to test stress Git? Almost. So in here, we have a group of like a regular activities that will perform or prepare for our project. But I would rather focus on the part that it's not mentioned that often. So limitations, they're always there. So we either don't have time, we have resources, we don't have knowledge. So basically, we need to come up with a solution. And that solution comes through scaling. So sometimes we are not able to test on the production-like environment. So we need to basically come up with a replacement for it. And of course, to validate our results, we would like to have some comparison. And also with the analysis, the requirements are easy. Like either they're met or not. It's binary result. However, we would also like to point out the things that are problematic. I mean, what doesn't really matter if it fails? I would like to know how to improve it in the future. So my requirements were I would be limiting myself to standard CLI Git operations, so nothing fancy. And regarding the time requirements, I would be using something as a reasonable time. And this is the magic keyword, because in my opinion, the time limit should be as whenever you start thinking that this process takes too much, that's already a limit for you. And also, there's a mention that we subconsciously think about the more complex tasks. So if we are assuming that, okay, this is a simple task, so why the hell I'm spending like 5 minutes on it? On the other hand, if we are formatting the entire hard drive, we are fine waiting 10 minutes because we know that kind of seems like a lot of work to be done there. Okay, and the last point is actually I'll be using regular equipment. So it's not like I will be using a cluster or a cloud, like a regular day-to-day machine. So in here, I came up with some strange rule of 1-10-10, meaning that within 1 second, I would expect the simple commands to be executed, nothing less, nothing more. Within 10 seconds, a bit more complex that are being executed not that often. And on the last group, with the 10 minutes, I would like to finish the tasks that are run very rarely. Okay, so regarding the test data, I also wanted to ease my job because the scenarios are endless. So I decided to actually limit myself to linear growth of the repository. There are no peaks, there are no cycles like in the sprints where there are periods where we are not committing anything. On the other hand, every file would have unique content. And also with the number of files per each directory. I know that there are a lot of moving factors within, and I decided to just limit it to 1,000 files per directory. And honestly, I don't care about the commit details. I don't care about the committer. I don't care about the author. I don't care about the message in the commit. Also, I don't care about branches, because basically on the local setup, they're almost non-existing. I mean, we of course have it. It's not on the scale. We don't have 2,000 branches on our local setup. And in order to bump up the number of Git objects, I also decided to increase the number of files committed per each commit. I'll talk about it a bit later, but for now, you should also know that there will be 2 levels of directories. And that's actually something that I've added later on, as it was a bit problematic to create the data and the trees inside. And the files would have a static size. So no modification or no appendments, just take the file, replace the content with a new unique content, and just commit it. Okay, regarding the measurements, Git comes with a very nice mechanism. It's called trace2, and it offers a lot of insight into how Git works. Frankly, it's quite good. The only problem is that handling is not necessarily the easiest, at least in my setup it wasn't. So you can imagine that you can either set it up through the global variable or environment variable, or you can do it with the git config. The only problem is that if you have multiple repositories to test, everything lands in the same place, and it's kind of not that easy to parse on the first glance. So you can see that I've highlighted basically the start of the Git status and the end. So you can imagine that with the more complex command, it actually grows a lot. So on the other hand, let's focus on the system-wise. So on Linux, we have multiple options. And on Windows side, we have actually 3 of those, which are, I think, more than enough, with Performance Monitor being the most complex one. And it's still, personally, I struggled a lot configuring it, especially if you would like to track the process. That does not exist and spans only for a few seconds. So in here, overall, I stick with the simplest approach, the time function. Okay, what about the test engine? Usually, we talk about test engines as something that it's a massive. And that was slightly different in my case. I basically used something very small, and I decided that if I'll need more, I'll create something more. So in here, you can see that the time function was wrapping the actual Git command. And the time has a nice feature of writing its output to standard error. So it's enough to grab that, redirect to the file, and then collect the results. So from something like that, I moved to more digital version, and that could be actually put into spreadsheet. And also with the time, we have actually 3 options, and I will be focusing on the real part only, as this is actually the time I care about. I don't really care if the process was spin up multiple threads in total take 10 minutes. I care about the fact that the command finished within 1 minute. Okay, and as a part of the evolution, the whole test engine grew a bit, because at a certain point I decided, okay, I need to speed this process up. I have multiple repositories to test. Let's do it a bit faster. Okay, so the system under test, usually see the same concept. However, in reality, it's slightly different, because in here, I'm focusing on the machine itself. So on my hand, I had 2 daily drivers, and usually I'll test them both. However, we can see that on one hand, you have a kind of a new machine, 11th gen core processor. On the other hand, it's a 2nd generation. And of course, on one hand, we have NVMe drive, on another SSD. Windows 11, Windows 10. Cool, it's just that there are too many differences, and I'll be basically digging myself into the whole blob of test results, and then I'll need to think out something smart about those. So before we'll jump into the generation of the commits, I'll need to bore you even more with the Git objects. So in Git, we have 4 different objects type. And today, we'll be omitting the tag one. So if you take a look at the commit itself, each commit has a reference to the tree. And we should understand tree as a mapping of our current working directory. And you can see that if we actually take a pick inside the tree, we'll see it's actually mapping directory and listing all of the blobs, which are regular files or another tree. So in this case, if we take a peek at the README, yeah, nothing special. And also, if we take a look at the tools, it also lists those 2 files. Okay, so to the core part. And frankly, that part was the most terrifying, most nerve-wracking, and the most time-consuming part of the whole project. So basically, there are no such big repositories on the market, at least in the open space. The biggest one is the Linux kernel repository with 1.2 million commits. So I needed to generate something from scratch. So I was also aware that I'll be failing multiple times, meaning I was certain that after generating the data, there will be something wrong with it. I would have some strange result that does not make sense. So I decided that it needs to be fast to generate, so under 24 hours. And also, I didn't want to have any surprises, so I decided that this process needs to be deterministic one. Okay, so started small with just a bash script that would generate 10,000 empty commits. And it took 7 minutes. Not that bad, not that bad. Okay, so with the 22 commits per second, it would take 10 days. Yeah, not bad. Not bad, not actually, to be honest, it was terrifying. So on the other hand, I've started with the JGit, so Java implementation. I feel way more comfortable with Java. So I decided, okay, let's try that. I've also started with empty commits. That was way better, 3 minutes. But it would still take almost 2 days. So I decided, okay, it's not going to work. However, I will still keep pushing and just see how bad it will become. So with the random content of the file, I generated in under 10 minutes, and I knew it's going to be bad. So at that point, I started looking for something a bit more lower level, like let's go back to the core, to the C, and I've started investigating the libgit2 library. So it's actually an open API for Git written purely in C, and it's basically a standalone API. So I started also with empty commits on the old machine, and 41 seconds. That was a brief flow of error. 240 commits under 24 hours. Perfect. Although there were basically empty commits, so I was still far from the target. Then I pushed to a new workstation. I decided, OK, let's bump it up to a basically more real-life scenario. With that, I was able to still generate it under the 10,000 and slightly above 2 minutes. And it still was not enough. So then suddenly I decided, OK, probably I'll need to move it to the cloud, generate it, and then I can continue with the tests. So before doing that, and of course paying for the cloud, I decided to just take a try on the WSL. So with WSL, I was astonished. So 47 seconds, and I was able to do it in 26 hours. And I was almost there, because I thought, OK, it's still taking too long, but then I could generate multiple repositories and then merge them together after all. But there was a catch. So when I was generating those commits, Git created a list of objects. And frankly, it's enough, but it's not the default state of the repository. If you clone the big repository, you don't have a mass list of files. You have a nicely packed file with an index. And that process, actually, that process of packing is part of the Git garbage collection. And it's one of the most process-consuming commands. So in this case, I knew that there needs to be something else, because I will be basically generating commits and then packing them together. And while researching the topic, I found out that there is actually a tool that might be useful. And it's called fast import. And it's built in Git. So the idea is that the tool is being used whenever we are migrating from one repository type, like SVN, to Git. Git to SVN is actually built-in, and it's actually a front-end application. So with the documentation, it's exactly what I needed: import large repositories with minimum amount and time. So how it works is that this front-end application needs to produce something on the standard output, and then basically Git fast import will collect it and read it out. And you can see I've highlighted few of the commands, like the blob will create a file, or the blob object. And then with the commit command will define what should be there in the commit and also the list of the blobs. And that was kind of perfect for me, because I already had almost the structure ready, just need to swap the tools. And the fast import actually has an alternative use. So in this case, I would like to show you the example with removing the jar. So then, first of all, we'll export entire repository. We'll filter out all the jar files and all the garbage that we have, and we'll create a new repository. So the idea is that whenever we touch something inside the commit, we'll change it hash. So basically, it's a totally different repository that looks exactly the same. However, the end user will not notice any difference. Basically, all the branches will be pointing to the same location. All of the commits will be named the same, created at the same time by the same person. The hashes will be different, but the repository will look like exactly the same. So final results were, when I actually bumped it, ran it on the WSL, I was able to generate the entire 20 million repository below 3 hours. And it was whopping almost 2,000 commits per second. So one challenge done, more ahead. So in this case, I also needed a bit more data, because I generated the repository, OK, it's fine. But how it compares to the real ones. So in here, I've created the 20 million commit. I called it fat, because for me, it was already fat with 100 gigabytes of the whole repository itself. So I picked the Linux kernel, the biggest one I could find. And then I've also created my own version of it, so also 1.2 million commits. And I decided, OK, so this is one spectrum. I would like to also pick something a bit smaller. So I got with 100,000, of course. And in order to be able to scale properly, I also found the C Python repository within the same size. And of course, I got my favorite one, the 1. So this is actually the 3 commits, and I was stealing the files from the 20 million commits and 1.2 million commits, committing them together, and I had the same number of files and whopping 40,000 Git objects. OK, so in here, there's one point to mention, is that not only we have different number of files with the Linux kernel and C Python, but there are also some garbage in it. I call it a garbage from the Git perspective, because you can see that the green one is very nicely and neatly organized, the small files. But with the C, Python, and Linux, especially with Linux, we have almost 100 files that are way above 1 megabyte. Okay, so let's jump into the actual tests. So I started with git clone, and already there was a first failure. So in this case, with 20 million commits, basically the command crashed after several hours. And the idea was that most likely it was the fault of the Git server I set up locally, meaning that Git server seems to be loading up every object into memory and then serving everything to the user. And especially even with the Linux, I was barely under the limit of 10 minutes that I mentioned earlier. Okay, so with git index, that's something I haven't mentioned, but the index is actually a bare bone of each repository. So every action that we make almost is affecting index by some means. If we add a file, we are actually updating the index to include that new file there. So in here, in case of a Linux, yeah, the results were not looking pretty good. So we could expect that if we have massive changes, the Linux will perform worse than those 3.5 seconds. So with the status, oh, that was easy. Basically, all excelled, nothing to worry about. Moving on with the checkout. So with the checkout, it's a bit more complex, because then Git will try to look to the commit that it's 10,000 commits behind the head, take all of the files from there and move it to the current working directory and update the index. So you can see that for Linux, it's way more than this 3.5 seconds. However, surprisingly, the 20 million commits are still under the 1 second. So where's the difference? What's the actual matter? And of course, jumping through another one with git diff, when we are actually comparing the result. This is not the command we will, it's not the version of the command we'll use on a normal basis. No one normally sane is doing that on the command line, because the output is enormous and boring and it's hard to parse. But the idea is that the tools that might be using directly Git, like the IntelliJ, might actually be parsing that results, comparing the two branches. So in here, Linux is not, the Linux repository is also not that good. But going back to the commands that are more natural and more day-to-day with the git add. Generating a small file, adding to the index, already fractions of the seconds, nothing to worry about. On the git commit, it's also blazing fast. So where's the catch? Okay, let's start with the pushing changes. Okay, but then there's nothing wrong about it. Okay, so then moving or pushing all of the commits to the repository. And here the problems are starting again, because Git will try to also load up everything to the memory and push it to remote repository. And in here you can see that it's a very nicely output. The process was killed by the system after 17 hours. And you can also see that the actual real time is 17 hours, but we spent 30 minutes on actual doing stuff. And that was caused by lack of RAM. So the system entering the panic mode and trying to save up as much as memory as it could, trying to move the memory into swap partition. And doing that over and over was slowing down Git as hell. So with the garbage collection, it was even worse. Basically, even for smaller repositories, it was taking also significant portion of time. With the increment, so I will explain why or what does this increment mean. But in reality, it's the smallest package of files or objects that Git could actually process in one go, and it already took half an hour for 20 millions. Yeah, and the full one actually failed also miserably, with 2 attempts at least. Okay, so overall, it wasn't looking that bad. With 20 million commits, we failed in only one category, with the garbage collection and with the push, the clone. But it's not looking that bad, to be honest. What about the limitations? So as you probably saw, the limitation was actually the RAM and the garbage collection and the Git server. So those needs to have beefy machines. And it's no wonder why GitLab or GitHub are limiting the size of the repositories that people can create. And I believe it's around a few gigabytes. So you can imagine how powerful the machines they need to have there. And also the size of the disk. You saw previously that a single copy of the repository was 100 gigabytes. I would say not that much. However, if you consider that NVMe drives are not that big, how many copies I can have? And of course, the system, the programs, there is not much wiggle room there. And of course, there is a ticking time bomb. Usually, I mean, we could work day to day and nothing would happen. But then Git has a very nice mechanism that will actually, on the long run, will kill us. So in this case, every operation like commit, merge, fetch would actually trigger the garbage collection with the auto flag. So what it does, Git will check, oh, is it already a number of loose commits, or sorry, loose objects that is worth packing? Okay, I'll do so. And that's pretty fine. For the 20 million commits, it actually took half an hour. And this process is actually done on the background, so you're not affected by it that much. Although, if we are reaching the limit of 50 packs, then Git will say, okay, it's time for a proper cleaning. Let's do some stuff together. And that will actually cause a problem, because it will actually be running for a long time, will consume a lot of memory, and nothing useful will be produced after that. So, with the conclusions, it seems like the number of commits overall or number of objects does not matter really that much. However, we could see that potentially the repository health is something that it's more affecting the times. And of course, with the garbage collection and the Git server, we need proper machines to do so. The next steps would be that we would, or at least I would like to scale down with the number of commits. I don't really think that it's that much of a problem looking at the results. I would be rather focusing more on the number and the size of the files, like how the whole system would be degraded if we start pushing some garbage into it. And also with the huge monorepositories, Microsoft came with their own fork for Git. They're actually addressing the huge monorepositories with the tool that they call Scalar. So that's definitely something worth seeing. With Git server and basically version control hosting, it also might be interesting to see how GitLab or GitHub can handle such repositories. Officially, they don't, because basically any attempt to push a bit more to the GitHub ends up with the GitHub support team blocking the access to the repository. So, and of course, IDE and tools. So now I have the repository. I could actually try to break the other tools with it. And of course, something that I haven't had time to test properly, but there is also a file system daemon that will help with those operations and will notify Git which files have actually been altered, so the old operations can be done even faster. And that would be all, so thank you very much. And all of the files or the extras you will find out under that link, also the feedback form if you like something or you didn't. Yeah, thanks. Do we have any questions?
Dziękujemy, Paweł. Oklaski mocne. Nie jest łatwo poprowadzić techniczny temat, a tym bardziej po angielsku jeszcze, żeby to wszystko dobrze wytłumaczyć. Bartek, masz pytanie, tak? Już lecę do ciebie.
Jasne.
Przede wszystkim wielkie dzięki za tę prezentację. To jest naprawdę dobrze oparta na danych prezentacja z fajnymi wynikami. Tak się zastanawiam tylko, ponieważ rozumiem, że problem się pojawi mniej więcej, gdy będziemy mieć repozytoria 10 razy większe od największych używanych obecnie. Czyli to jest takie trochę przewidywanie, co się wydarzy w przyszłości. Jaki jest rozkład obecnych rozmiarów? No bo rozumiem, że Linux wyznacza tu tam prawdopodobnie górne, rozsądne ograniczenie. A jak z pozostałymi takimi dużymi repozytoriami? Czy to są tej samej skali, czy znowu są mniejsze niż Linux, więc to by odsuwało nam ten nasz doomsday trochę w przyszłość?
I tu zaczynają się schody. Tu się zaczynają schody, bo jednocześnie mamy bardzo małą liczbę repozytoriów, które są dostępne publicznie. I tak naprawdę gro tych wielkich repozytoriów to są repozytoria prywatne w korporacjach. Wiemy o tym, że Google ma swoje repozytorium, Facebook ma swoje repozytorium, Microsoft też próbuje swoich, więc tak naprawdę ciężko jest mówić o jakichś danych konkretnych. Przy GitHubie są statystyki, natomiast większość tak naprawdę wydaje mi się, że użytkowników GitHuba bardziej interesuje popularność repozytoriów, a nie ich rozmiar. Więc bardzo łatwo jest wyszukać najbardziej popularne repozytoria po liczbie gwiazdek dodanych. Natomiast po wielkości tego tak naprawdę chyba nie jesteśmy w stanie zmierzyć.
Dlatego też myślę, że być może pojawienie się nowego narzędzia nie jest aż tak pilną potrzebą i ono się nie wydarzy, myślę, w takiej przewidywalnej, w krótkiej czy średniej perspektywie. Powiedziałbym tak, w momencie, gdy SVN dominował i pojawił się Git, to był rzeczywiście przełom, bo on po prostu rozwiązywał wiele takich podstawowych problemów, które SVN posiadał. Widać zresztą, jak SVN został wymieciony ze sceny. Natomiast w przypadku Gita większość tych problemów jest dobrze rozwiązana, a architektura jest na tyle dobrze przemyślana, że da się znaleźć obejście, tak jak z tym daemonem, tak? Który po prostu pewne rzeczy będzie nam na bieżąco. Dlatego moje pytanie do ciebie, czy sądzisz, że faktycznie w najbliższych, nie wiem, 10 latach możemy się spodziewać następcy? I drugie pytanie, co ten następca miałby robić, czyli jakie problemy miałby rozwiązywać?
Tutaj wydaje mi się, że następca, jeżeli się pojawi, to nie pojawi się zbyt szybko i z drugiej strony myślę, że będzie odpowiadał na konkretne problemy użytkowników, a nie systemu. Bo przyznajmy szczerze, że Git nie jest najłatwiejszym narzędziem. Oczywiście po kilkunastu latach praktyki jesteśmy w stanie sobie poradzić z pewnymi problemami, ale to też zależy od naszych teamów, bo też zauważyłem po sobie, że jeżeli pracuję w takim dojrzałym zespole, tam my nie mamy żadnych problemów z Gitem. Natomiast jak pracowałem w projektach, gdzie dopiero Git był wdrażany, tam było pełne pole do popisu. Takie akcje odchodziły, że po prostu to się w głowie nie mieści. Więc wydaje mi się, że kolejnym etapem byłoby przejście Gita w trochę bardziej naturalny język, gdzie większość tych akcji będzie tak jakby pochodziła od IDE.
Czyli interfejs GPT.
No, zobaczymy. Zobaczymy.
Jeszcze raz wielkie dzięki na radosłową prezentację.
Dzięki. Jeszcze jakieś pytania od kogoś? O, pięknie. Dobrze.
Paweł, ja bym się spytał w sensie, jaki jest cel tych pomiarów? W sensie, czy szukacie miejsca, gdzie optymalizować, czy po prostu chcesz udowodnić, że na razie jest to po prostu narzędzie, które optymalnie się nadaje do tych zadań? W sensie, co ma na celu całe jakby to ćwiczenie? Bo jeszcze szukasz innych case'ów, które chcesz robić. Chcesz się przygotować na przyszłość.
Wiesz co, chciałbym zobaczyć, gdzie są limity tego Gita. Chciałbym zobaczyć, czy faktycznie, czy rozmiar samego repozytorium ma jakikolwiek wpływ. Natomiast się okazuje, że o to możemy być w miarę spokojni, natomiast powinniśmy więcej uwagi pokładać w to, co my wrzucamy do tego repozytorium. Bo prawda jest taka, że jeżeli coś raz wyląduje w repozytorium, to jest tam na zawsze. Przez 10 lat co najmniej nie spotkałem się z sytuacją taką, że projekt powiedział, wiecie co, my teraz tą historię całą wywalimy, bo tam jest dużo śmieci. Jedyna opcja, o której pamiętam, to było jak przechodziliśmy z SVN na Gita i w tym momencie był problem taki, że potrzebowalibyśmy kilku tygodni na przeniesienie repozytorium. I wtedy padła ta decyzja, ok, dajcie spokój z historią.
Dobra, dzięki. Zmieścimy jeszcze jedno pytanie.
To kiedy się możemy spodziewać części drugiej z mniejszą liczbą commitów i większą liczbą plików?
No, tutaj też jest skomplikowana odpowiedź. Przyznam szczerze, nie wiem. Też musiałbym się upewnić, że taki temat byłby dla większej ilości osób interesujący. Bo przyznamy szczerze, że no, to nie jest temat bardzo mocno popularny i tutaj już wchodzimy na terytorium, gdzie tak naprawdę bardziej zainteresowani mogli być sysadmini albo opsi. gdzie tak naprawdę ta narracja byłaby skierowana. Są specjalne w ogóle prezentacje wyłącznie skupione na gicie i całe konferencje, więc może tam coś takiego by znalazło zainteresowanie.
Ale z racji tego, że w sumie przeprowadziłeś to jako international po angielsku, to w zasadzie
Zobaczymy.
mógłbyś temat uderzyć, nie?
Zobaczymy.
Dobra, dzięki wielkie.